Okay, so welcome to Module 12, Game Theory in Blockchains, and this is Lecture 1, which defines the basics of game theory. And we're going to deal with these topics: game theory definition, and some other extra definitions about game trees, information sets, and so on. The idea of this model is that you know the basics of game theory and that you can identify some situations in which game theory can be used in our blockchain systems. So the learning outcomes specifically of this lecture are the definition of the basic game theory concept, the definition or explaining how we can represent games with game trees and see the decision points, decision nodes, and information sets, and related and some more related concepts. And finally, also see strategies and the strategic form. So let's go to the definition of game theory. And game theory can be defined as it's a theory that studies strategic interactions. So there are interactions. Here we mean that we have at least two entities, two decision makers, that they interact with each other. So we need at least two or more people. And the interaction is strategic. This means that when one party makes a decision, this decision affects the utility of the other party. For example, a non-strategic scenario is a perfectly competitive market. For example, a market with many sellers, many buyers, and in this case, essentially, what one party does does not affect the market. In this case, we say that we are in a non-strategic environment, but in the case of game theory, we deal with these strategic environments. What do we have to define, or how can we represent these strategic interactions or games? To do so, we need to consider different aspects. For example, how many players do we have in our scenario? Which actions can these players do? Or which is the available information when we need to take an action or a decision? And finally, which are the outcomes after we play the game, doing certain actions or movements? To represent all this information, we have this way of representing this, which is called the extensive form representation, or also this is commonly known as the game tree representation. In this game tree representation, as we see, we represent our strategic interactions or game as a tree. There are no cycles, as you see here, and at each node of the tree is what we call a decision node, and each decision node in the tree belongs to a player. For example, here we have 3 decision nodes in this tree. The first decision node belongs to player 1. So player 1 essentially here needs to decide which actions to perform, in this case A or B. So player 1 can play A or can play B. There is another decision node by player 1, which is this one here. And at this point, the player 1 can play E or F. So these are the 2 decision nodes in this tree that belong to player 1. On the other hand, we have also one decision node in the game tree that belongs to player 2. And in this case, player 2 can play C or D, as you see here. So we are representing here all the game tree represents all the decision nodes, points in which, in other words, points in which a player can take an action and should decide an action. And finally, we also in the tree we also put the outcomes of that result from each player playing one certain action. So this is also represented in the tree, as you see here. In the leaves of the tree, we represent the payoffs for all possible game outcomes, depending on all the possibilities, or all the possible actions that each player can play. As you can see also, the game tree is also representing the sequencing of this, the sequence of actions, in fact. So here first, as you see, the first decision has to be made by player 1, and player 1 can choose A or B. And then is the turn of player 2. So now player 2 can play C or can play D. And now again is the turn of player 1 again, and can play A or play F. So the game tree here, as we see, is also representing the sequence of possible moves or possible decisions that each player can do. However, there are games in which some movements, for example, are simultaneous. So, and in this case, we need a way of representing this fact in our tree. And for this reason, it appears the concept of information set. So, an information set is a collection of decision nodes in which a player cannot distinguish between, because the player doesn't have enough information, doesn't know, for example, which was the decision of the other player. So as we will see, then we need to define the concept of information set. Let's see this with an example. And in this example, here we have our information set. Okay. In fact, each decision node is also an information set. So, well, in fact, here we have an information set or decision node. They are equivalent. I mean, in this case, the information set has just one decision node, and the first information set is for player 1. As I said, this information set is made only of one decision node, and the decisions that player 1 in this case can perform is A or B. Okay, well, on the left, if player 1 decides B, well, player 2 can play A or F. Well, this is as before. Then we have another information set made of just one decision node, in which player 1 can play C or D. And the interesting part comes now, because player 2 now has to perform a decision, but player 2 doesn't know which was the decision, which was the previous decision of player 1. In this case, player 1 doesn't know if player 2 doesn't know if player 1 played C or played D. We don't know. Okay, so we don't know if we are in this point of the tree or in this point of the tree. In fact, and this is the way in which we the picture in which we depict this situation. So let me draw it again. So player 1 plays C or plays D. If player 1 plays C, we will go to this node here, to this. And if player 1 plays D, we will go to this node here. But player 2 doesn't know which was the decision, if C or D. So from the point of view of player 2, we, with this dash line, or sometimes we encircle these two decision nodes, we encircle them or create a dash line to represent that player 2 doesn't know which was the decision of player 1, if C or D. So for the point of view of player 2, we are at this level of the tree, but we don't exactly know what happened here. So in this case, we say here that this is an information set that is made of two decision nodes. And we cannot distinguish between these two decision nodes because player 2 doesn't know which was the action performed by player 1. Okay, so in general, many information sets only have one decision node, but when we don't have enough information, then it starts to happen that we can have information sets made of different or multiple decision nodes, as this is the case. As you see here, the actions of each information set must be the same. Okay, so from this information set, player 2 can play G or H. Okay, as you see here, we can play G or H, and we don't really know if we are in this node here or in this node here, but from the point of view of player 2, we are in this information set, which is the two of them, and the actions that you can do now are the same whether you are in one node or the other. Essentially, we don't know in which node we are, but here you will see that the actions are always the same from all the possible decision nodes inside an information set. And finally, well, if the game has perfect information, if players have perfect information about the actions of the other player, then each information set has just one decision node. Okay, but this is not the case when we have not perfect information, which is as in this example. Let's, for example, as an example now, let's define some situation and then let's try to figure out which is the game tree and try to do the picture and also try to see which decision sets or which information sets do we have and so on. And the example is the following. So let's consider a scenario in which we have two players, player 1 and player 2, and player 1 has a certain amount of money and he's considering whether to buy Ether or and stake it, or is also considering about investing in creating a distributed application. Also, if player 1 decides to do the distributed application, he is thinking in doing so in Ethereum or in Cardano. There is another player that is in a similar situation, but player 2 in this case, for sure, he is going to create a distributed application, so is not thinking in staking, only in creating the distributed application. And the only doubt that player 2 has is to either deploy the application in Ethereum or in Cardano. The idea is that player 2 will not be able to observe if player 2 is staked or not. This is our setting. And here we consider that this is a strategic interaction because the distributed applications that these two players are creating are very similar, and they are competing with each other. And also there is an impact in regarding in which network the application is deployed. If both deployed on the same network, they will compete for users, and they will be well, less. It will be worse for both. So yeah, let's depict this situation, and this is the idea. So player one has to decide if stake or not to stake the ether that he obtained. Okay, as the in our example, we say that the player 2 doesn't know what player 1 has decided. So at this moment, so we don't know. Player 2 doesn't know if player 1 stake or not. So this is why we are in this tree. These two decision nodes are included in the same information set, because whether player 1 staked or not is unknown for player 2. So now player 2 can decide to deploy the application or deploy its application in Ethereum or in Cardano. So remember that from any information set, always we have from the decision nodes of each information set, we always have the same, we always need to draw the same possible actions. Okay, so from this, if the previous player didn't stake, thing that I don't really know, being player 2, well, anyway, what I can do is deploy my distributed application in Ethereum or in Cardano. If player 1 stake, okay, but it's okay. Anyway, I don't know this, and my actions again can be deploy my distributed application in Ethereum or in Cardano. So after player 2 performs his action, then it's the turn of player 1 in case player 1 didn't stake. Now player 1 is going to deploy its application. In this case, I'm assuming that player 1 is observing where player 2 deploy the application. So in this case, this is not an information set. These are different information sets. Okay, it's because player 1 knows exactly what player 2 did in the previous movement. And now player 1 can deploy its application in Ethereum or in Cardano from this decision node, and also from this other decision node, player 1 can also deploy on Ethereum or in Cardano. Notice that we are using primas here to clearly put a different name for each action depending on which information set you are taking the decision from. So, and this is the typical and the easiest way of naming actions. So actions always have different names if they are taken from different information sets. From now on, I'm going to use the term always information set. Okay, information set may be made of just one information of one decision node. Okay, but from now on, I will just consider information sets, whether they are done from one decision node or from multiple decision nodes. And then in the game tree, in each leaf of the game tree, we put some, in this case I'm putting letters, but in general these are numbers. In our game trees, we also express in the leaves, we express which are the outcomes. After each player plays whatever actions. he decides to. And in this case, for example, let's see the preferences for player 1. Okay, so J in this case is the best. I'm considering this would be a number, J, and I'm considering that J is the best outcome possible for player 1. Okay, because I'm considering here that the best possible outcome is when player 1 deploys in Ethereum and player 2 deploys in Cardano. Okay. The next best option for player 1 are M and N because, well, the next best option is to stake, for example. I'm considering that this is the most profitable action after deploying alone in Ethereum is the best one, but after this one, okay, staking is the second best. Okay, then it goes Y, which is deploying alone in Cardano. It could be the next best option. Then it goes X, which is deploying together with player 1 in Cardano, in Ethereum, sorry. This is the next best option. And the worst possible result for player 1 is ending with its application being deployed in Cardano while player 2 is also deploying in Cardano. Okay, but this is just an example of how can we order our preferences. Now, these preferences are just letters, but in general, we put some numbers here. And it is not a single value, it is a multiple value array in which each position of the array is the outcome for one of the players. So in this case, I can put numbers and say, okay, the best option for player 1, it wins 50, I don't know, 50 could be millions of euros or whatever you want. Okay, in this case, I'm saying that if player 1 is playing, in this case, what is playing player 1 is playing not to stake, and then Cardano, player 2 is playing Cardano, and player 1 is deploying Ethereum. So if player 1 plays these actions while player 2 play to deploy it in Cardano, then the outcome is 50 for player 1. For player 2 is just 20 in this case, for example. Okay, well, let me discuss rational behavior in just 1 minute, but before let me discuss the concept of strategy. And a strategy defines an action for each possible information set of a player. So a strategy, a concrete strategy, is just the definition of which action you are going to take at each of your possible information sets. And let's see here an example. Let's observe this game here, and let's see which are the information sets for player 1. Player 1 has these information sets. So the strategy defines an action for each possible information set. In this case, player 1 can play 4 different strategies. Can play A at the first information set and C at the second information set. Can play A at the first information set and D at the second information set, and so on and so forth. So here we have 4 possible strategies for player 1. These are the 4 possible strategies of player 1, and we call this set the strategy set. Okay, the strategy set is the set of possible strategies that a player can follow. And for player 2, there is only one information set. It's true that this information set is made of two decision nodes, but it's just one information set. And from this information set, player 2 can only play two possible actions, which is E or F. So for player 2, the possible strategies are only E or F because it only has one information set, and these are the two possible actions from this information set. Strategies are very important because they allow us to represent our games instead of using a game tree. We can alternatively use the strategic form, or which is also known as the normal form. So in the normal form, we create a matrix in which at rows and columns we put all the possible strategies, or we name all the possible strategies of each player, and then at each cell of this matrix we put the outcome that results after players follow their corresponding strategy. So in this case, if player 1 is following the strategy A, D, and player 2 is following strategy E, then the outcome is 3 for player 1 and 3 for player 2. So we are going to denote that as S1 all the possible strategies, or the strategy set of player 1. S2 is going to be the strategy set of player 2. And then let's see another example. Is the previous, is very similar to the previous example, but we remove this information set. Here is a variant of the previous game, but in this case, player 2 knows the decision in this second information set of player 1. Okay, so let's see which is how now this information set is. Let's see now how the strategy set is modified now. Okay, so essentially it's this game, but we're going to remove this dash line here, which means that now player 2 will know the decision of player 1 in the second information set. So it's just, well, the idea is, okay, we remove this line here. Okay, so now player 2 has two information sets, each made of just one decision node. So now the strategies possible, possible strategies for player 2 need to consider two information sets. Okay, so player 2 can play E or F at this information set, and also can play E or F at this other information set. Okay, so now the possible strategies of player 2 are play E on the first information set and play E on the second information set. Okay, but and the last thing to consider here is that well, it is not enough we remove the dash line. In general, we like to make actions explicit for each information set, meaning that we usually take different names for the actions that go from a different information set. So like this, like here. Okay, so this is an information set. the actions from this information set are E and F, and this is another information set, a different information set, and the best way to depict these games is to choose different letters for these actions. So it is really clear that these actions are the ones from this information set and not get confused with this other information set. So it is a good practice in general to select different names for actions that take place in different information sets. So then our matrix of possible strategies of strategy sets, in this case, is like this. I mean, player 1 has two possible actions because it has two different information sets, while player 2 has also two information sets and needs to provide an action for each of these information sets. So resulting this matrix here. Observe also that here the matrix is like complete, and this is the best way of expressing this matrices or this normal form representation of games. It is true that after player 1 plays B, well, no matter what happens, the outcomes are going to be 5 for the first player and 5 for the second player. But in general, it is a good practice to define as a strategy defines all possible actions for all possible information sets. So, after playing B, okay, you are not going to play anything else, but the idea here is, okay, it is the best way to represent the matrix is to make it complete, meaning, okay, in the second information set of player 1, we can play C or D, okay, and repeat here we repeat the outcomes, okay, just to don't have a matrix with holes. Okay, everything is filled here. And I'm sorry because there is a mistake here, because if player 1 plays B, whatever is played by player 2, yeah, we have 5, 5, 5, 5, 5, 5 everywhere. Okay, now let's go with more definition. Let's see what is a strategy profile. A strategy profile, a concrete strategy profile, is a vector. It's a vector of strategies, and in general, for a subset of players in the game. But well, let's do it in particular. Let's create the strategy profile for all the players in the game, in which each element of the array is a certain strategy followed by this player. Let's see an example. And in this example here, well, it's our previous example, by the way. Okay, well, there was a mistake here, which is 5, 5, 5, 5, 5, 5, 5, 5. And here we have the player strategy sets is for player 1, and we denote it as S1. The strategy set, the possible, all the possible strategies are these ones. And remember that each strategy decides one action for each decision node. So the strategies of S2 are these ones here. And a strategy profile is just selecting one possible strategy for each player. For example, player 1 can play BC, while player 2 can play EF prime. Okay, so this is a strategy profile, a concrete strategy profile where each player, we are considering one strategy for each player. We can also define the profile set or the strategy profile set, which are all the possible sets that we may have. And this is just the Cartesian product of all the strategy sets of each user. So in this case, it's just taking the product. So this is one strategy profile in which player 1 is playing AC, player 2 EAE prime, then this plays AC and the other one plays EF. I mean, these are all these possibilities. Okay, so if this player 1 plays this and player 2 plays this, player 1 plays this and player 2 plays this, player 1 plays this and player 2 plays this, and so on, all the possibilities. All the possibilities is what we call the strategy profile set of a game. And now, we have the payoff function, which is another concept of game theory. And the payoff function is a function that assigns a numerical value to each possible strategy profile of the game. I mean, we have a strategy profile, which means that there is a strategy for each player. So the idea is after each player playing a certain strategy, which is the outcome, okay, which is the outcome of this strategy profile. The payoff function assigns a value, a numerical value for each strategy profile, and that's it, essentially. These lessons went about many different definitions, essentially, about game theory. And the idea here is, okay, if we want to use these ideas in blockchain, I need a way of implementing some simultaneous moves in a smart contract. So the idea is to use this basic game theory to analyze smart contracts, and the idea is, okay, how can I simulate, or how can we emulate these simultaneous moves in a smart contract? Well, for this, because blockchain networks like Ethereum are sequential. I mean, you send one transaction and then another transaction, and each transaction must be executed and ordered before the next transaction is executed. So how can I create this idea of simultaneous moves? And for this purpose, you can create this simultaneity using a two-phase interaction with the smart contract, in which players first commit to their actions, but this is a commitment, so it is hiding, so you don't see, other players will not see which is the action that a certain player has committed to. And then there is all the players commit to their actions in one phase, and then in a posterior phase, after some time, then there is another phase in which there are transactions to the smart contract, just opening the commitments and showing which were the actions. So in this way, thanks to this two-phase mechanism, we can create the idea of a simultaneous movement in a smart contract, which is made of sequential transactions. Before going to the last slide, I just wanted to mention that we are going to assume in general, or it is assumed in general in game theory, that players play with rational behavior, meaning that they follow the strategies that provide a better payoff for them, and also that they know the structure of the game. They know what other players know and how they are going to behave. And this is what we typically call in game theory rational behavior, because you're going to pick up the strategies that provide you the best outcomes, given that you know the game, that you know that the others know the game also, and that you think that other players and yourself, you are going to play the best possible strategy to get the maximum payoff possible. Okay, so this is more or less it in this lesson about game theory concepts. And the idea in the next lesson is to discuss this scenario in which we have a strategic interaction. In this case, between a buyer and a seller. The seller wants to sell some product, and here we have a buyer that wants to buy it. And okay, we're going to create a smart contract for this interaction. And the interaction with the smart contract is a strategic interaction, because it involves two parties, and what one party does affects what the other party affects the outcome of the other party, and so on. So to conclude, well, in this lesson we provide some definitions about game theory. We also explain how to make a picture of a game using a game tree. Inside the game, in game trees, we represent decision nodes and actions. We also are able to represent information that we don't know, and here we use the concept of information set. And this information sets in general can be made by multiple decision nodes. We also define the profits, preferences, and outcomes. Apart from the game tree, we also saw this matrix representation of the game using the strategic or normal form. And finally, we discuss a scenario which is called the remote purchase, that essentially represents a game because it is a strategic interaction.